Welcome to the Bucky Call for the weekend of July 5th and 6th. Anne will not be joining us tonight. She's helping her daughter,
Hmm.
and it is the Calgary Stampede in up where Richard is. So he's laying low. He's hiding out. He doesn't want to get caught in the traffic, and he'll explain that, I'm sure. And it's the July 4th weekend in the United States. We're celebrating our 249th anniversary of being a country. Next year is going to be a big deal if everything goes as planned. And there's so much excitement on the front. So here we are. Joe, how are you feeling? And what do you anticipate getting out of today's call?
I'm feeling pretty good. It's good to be back. I know that I was away last week. I had a Stoic seminar in Greece, so I felt really good about that. It's one of those great experiences that um I hope I never I won't lose uh perspective and appreciation for the opportunity to go. So you know yeah, but there's a lot, I learned a lot, and it's amazing how systems thinking, and you can see, whether it be Bucky's thinking or even thinking of the ancient Greeks, and when people have frameworks and they're making coherent, um, coming to some kind of coherent conclusion as to for their decision making process, um, and kind of looking at the reasons behind um, their decision making processes, their ontologies, their epistemologies, you know their physics, as well as their logic. When you go through those things, it's really helpful in another number of domains, most importantly in life. And I think that's that obviously is what Bucky did. And so uh thinking geometrically is where I'm expecting to get a little, the same, to continue down our journey. And so that my expectation is to keep growing this call. Richard, how do you feel? What are you looking to take away from today?
Well,
Sorry
feeling
about.
pretty good. I've got a lot of, or not a lot, a number of sort of reflections to start tonight off, and in part, well, I guess in part because you just got back from Greece, so of course that always makes one think about the Platonic solids and what kind of evolution there's been since they first came around. But the reference to July the 4th, which of course is yesterday. Um, and moving into next year's celebrations, the thing that caught my eye on July 1st, which is Canada's Independence Day, um, is that on July the 1st is the anniversary year, if you want, of Bucky Fuller's death. He died July the 1st in 1983. 1983 was also the beginning, our declared beginning or official beginning of the partnership of four that eventually grew into the organization called Living Works Education. And I'm in my 84th year, but currently I am 83. So we had 1983 uh, uh, in terms of a startup. 1983 is when Bucky's, if you want, regeneration started, and this is, I'm still in my 83rd year, so that means that never again will there be 83, 83, 83 in terms of recognizing his departure. And of course, July 12th coming up will be his birthday, so we're kind of right in the middle of all this. The other thing that I wanted to mention, which is kind of connected to the looming celebration 1776, is that one of my colleagues in another group called World Weavers, he's kind of writing poetry, prose, and just the other day he wrote something about independence, and he says he started out with independence is an illusion, and I added to that and said that interdependence is all there is. Um, and I had some other things about um, undivided whole kind of reality versus divided whole. But it just struck me that I think, especially in coming into the 1776 anniversary, that not only do we in North America or those around the world have to start to appreciate that independence is an illusion, um, which really sort of, um, in a sense, negates the whole idea of celebrating the 250-year independence. It really should be a turning of the clock and a recognition that independence is an illusion, and all there is interdependence between, if you want to call it, sovereign nations around the world, or peoples, or organizations, or systems. Um, so I'm going to try and stick with this idea that independence is an illusion and interdependence is all there is. And there is no building block. And all that, again, one finds is a set of relationship patterns that bring us together and create the notion that we are in solidarity with each other, when in fact it's just a word that describes something quite different than what we really are in when we're working together. So that's how I'm feeling. Looking forward to having that reinforced with more of Amy's readings and get my picture back. Lee, how are you feeling, and what are you hoping to get out of today's session?
Well, we watched the fireworks last night, which were beautiful, but I kept getting sicker and sicker and sicker. And poor Steve had to put me to bed and leave me alone. I was so sick until maybe an hour and a half ago. I was sound asleep, and had to work at getting out of bed. He thought several times I was dead. So I am back to life now and excited about this meeting.
We're excited.
I missed last week.
We all did.
Yeah. Oh,
Well, we started out, we had to postpone it until this week.
aha.
I think at the time, Manu and I were the only ones trying to get on.
Oh, that could have carried on forever.
It was my problem. My alarm didn't go off. If you want to pass it on to me, Lee.
Steve, how are you doing? And what are you anticipating?
Okay, cool. It was my fault last week. If there's a fault, it was mine. My alarm, my phone went dead. I didn't even know it. And I have an alarm, that goes off an hour and a half in advance saying, get ready for Bucky. My phone was down. and it was sunny outside. What the heck? You know, and who expects it to be sunny at 9 freaking o'clock at night? And I'm looking out there right now, and the sun's about to go down, and in July. We're already past the solstice, so things are getting shorter, and life is wonderful. I'm contemplating your statements about independence and things, and I think I want to. I I love the idea of challenging this whole concept because Robert Sapolsky is big on the fact that there's no free will at all. He argues that, I think, rhetorically and scientifically, based on how the brain works, that um, before 20 or 40 or 50 milliseconds before a person becomes conscious of having made a choice, the brain has made the choice. And then the person has a sense of, oh, I chose that. Where actually the central nervous system actually locked in on it. Now, I can debate that for quite a while because in my book, I'm talking about stopping. And I'm talking about how stopping is the superpower. And admittedly, I have to practice stopping. And I do admit that my genetic code, in fact, gives me a degree of stoppability. But no matter how much stoppability I have built into my genetic code, I can get more by practicing. And that's a very subtle thing. But I think that there's a way to acknowledge independence. I like the idea that there is no independence. It's all interdependence. I really like that. At the same time, I have a choice about it. And so to that degree, I misname it when I call it independence. I maybe want to call it agency or stewardship or personal choice, something. So I'm really pondering about that because I do believe that there is no independence. One of our big problems in the world is somehow we think we can declare independence. And as soon as we do that, I think we hurt ourselves and hurt other people. But I am excited about the Constitution of the United States and the idea that we, unlike in the parliamentary systems, say like in Canada, the courts are part of the parliament. And I don't know about in Canada. You have to tell me about that, Richard, because in England, I think the Supreme Court is part of the House of Lords, which is one of the branches of the parliament. But I'm not clear on it. Are your courts independent?
Yes.
Good. So you modeled that. So you have a parliament, but you have also independent courts. And then you have
Yes.
independent from the legislature, right? And
Yeah, we're similar. The big difference between the Canadian and American parliamentary system, if you want, is that we have we have a parliament which is equivalent to the House of Representatives,
right on.
and we have a Senate that's not elected; it's appointed.
Uh-huh.
Um, and the Senate, by and large, is a rubber stamp of what the House determines. Um, and very seldom does it exercise its ability to challenge or send a bill back to the House.
Yeah.
Um, and so that's always very interesting in watching the dynamics of the parliamentary system within the two countries.
Right.
Um,
And yeah. And the prime minister is elected just like our president.
no,
Oh,
the prime minister is the head of the party that wins the election.
I see.
And so the prime minister comes with the majority in the House of MPs,
I get it.
members of Parliament. Um, and so in that sense, and the government too rises and falls on whether or not it has the vote of confidence in the House of Parliament. So you do not have an independent prime minister who can, who in a sense, sits outside of the houses,
Right.
the Senate and or the
Right.
House.
Yeah.
And so if the Parliament votes no confidence both within the bigger parliamentary system, in other words, all members are assembled, or there are particular kinds of committee structures that if there's a vote of non-confidence in that committee, the government will fall. Finance is one of them, a money bill.
Yeah,
And so when the government falls, so does the prime minister. Um, and
cool.
and
And you
then
actually use the term government falls. That's actually a political term in Canada because it does have to do with
yeah,
the vote of lack of confidence in the government falls. Okay, cool. So our Senate is elected independently, and then the House and the Senate have to bicker back and forth with each other,
right,
like they did over the big bill. And then the president is elected separately, and then
right.
the courts are appointed by the they're appointed by the executive with approval from the legislature, from Congress, um, who are supposed to
Our
give
courts are
advice and
similar in that
consent.
sense too. The courts are the judges are appointed by the prime minister
Uh,
or the governing party, and
how do you get rid of a bad Supreme Court justice?
um, I'm not exactly sure, but I'm thinking something similar to impeachment, or
Yeah,
um, that there is a process in which you can
yeah. So,
adjudicate a problem.
so once a judge gets appointed, they're kind of independent in their own realm.
Oh yes,
Okay,
they're
cool.
quite independent,
Good.
and we don't have the same election system down through the ranks that the U.S. does. So the dog catcher does not get elected. Uh,
Yeah,
the district attorney does not get elected. The
yeah,
all of those other sort of levels of election
yeah.
are not part of the Canadian system.
Okay. So anyway, I think our Constitution's pretty cool if it'll do more than hang by a thread. And what boggles my mind in American politics is how everything's focused so polarized on a particular party and so polarized on a president, and nobody is moaning and groaning about how ineffective our Congress is. If our Congress were doing the job, if they'd created legislation about immigration, if they'd created legislation on reasonable legislation on anything, but they don't. They haven't done anything other than pass a overspending budget for years. And I think if they were more effective, we'd have better things going on, but we rely on a president to issue executive orders, which is absolutely silly. All right, well, I don't mean to take this into a political thing, but I am pondering this independence thing. And now I'm ready to, oh, let me see. And so how am I feeling? I'm feeling pretty good. I'm looking forward to getting back into this. I really like like Joe was saying, I really like the conversation about these systems. I've been finding I found a neat thing from Jane. Richard, you sent me a thing on Jane. Jane has a seminar on phi in the solar system. I haven't watched it yet, but I'm very excited about phi in the solar system. And I already have my ideas about it, but I'd like to hear what he has to say about it. And a couple of other things that are pretty exciting. Where are we in this book? I have us on page 157 at framework of possibility. I think we started somewhere around there. And and we may have discussed it further down. Does anybody have you drawn a line um, in your in your book as to where we might be? Because I think we've done this octet trust thing. Maybe
Yeah,
not.
we have. I mean, we started there, but that's because that was the last time um, that I had led prior to the one that you had led. So we started with Octa Trust, and then we read and we did read through this. Um,
And we did
I
what?
think I think we're up
I
to multiplication by division.
You think we finished the chapter?
Yeah, I'm pretty certain that we
All
did.
right. All right, good then. All right, because when we start finishing the chapter, we go through the octet truss, and then we get down to discussing the lecture, then we finished oh, we did. And we talked about the buckyball and the lubricants. And I saw an excellent video on the difference between a diamond and graphite, which is pretty cool, and why graphite is so slippery,
Hmm.
which is because it talks about a lubricant here real fast. In contrast, carbon atoms in graphite are organized into planar layers of hexagons. So in other words, they're sheets, and their sheets are
Right.
separated by electrons, and the electrons allow the sheets to slide around. So I found a really cool thing on that. I wonder if you guys are interested, I could play it. I think I could find it pretty
Yeah.
fast. What?
Well, I was just going to add one thing. It's interesting in terms of the hexagon structure of the graphite, I guess, because that was a critical feature in the discovery of carbon-60. And when they were trying to put together a model of this new carbon that was unfolding, they had an image, at least one of them had an image of the geodesic dome in Montreal in 1967, the dome. But his memory had um, a hexagon image in his mind, and he thought it was kind of made up of triangles and hexagons. And so when they tried to get the carbon-60 modeling to curl so that it formed a sphere, they started doing it with hexagons, and the hexagons just kept going out and out and out like chicken wire. And then when the story goes that one of the scientists at Rice University in Texas went in to say goodnight to his young son, who was a great sports fan, and he had sports memorabilia all around his room, like baseballs and soccer balls and footballs. And when the father went in to say goodnight to his son, he noticed the kid's soccer ball sitting on a shelf. And right away, he realized that the soccer ball was made up of hexagons and pentagons. So he went back out and he restarted the modeling. And this is late at night now, after he got home from the meeting this was after the meeting that they had run into a stalemate. And so he put in a pentagon, and as he started to build it out, then it started to curl. And about 1 o'clock in the morning, he had this thing curled right into a full sphere, and he didn't know what he had. So he wrote a note, or I guess he didn't write a note then. He phoned the head of the mathematics department at Rice University, a colleague, and said, "This is what I found. What the hell is it?" And his colleague wrote back or phoned him back the next morning and said, "Well, I can explain to you what you really have in a geometric sort of way of describing it. But in simple terms, what you've just built is a damn soccer ball."
That's a
And
quote, right? Damn soccer ball.
well, the damn part, probably not, but it just
Oh,
said that
okay.
what you have is a soccer ball. And that's what led into the naming of the the structure, because apparently the convention is that if you discover something like a new kind of molecular structure, you can't name it after yourself. You have to
Yeah.
you have to give it some other name. So they were trying to figure out what to name it, and so they had the idea that there were and and the name is to it's called a fullerene, um, and the naming was such that so they thought, well, what about a soccerine? Then they went to football arene, and they went through a whole bunch of sort of sports like objects. And then finally, so, well, wait a minute, we actually got the whole idea out of watching this geometric sort of system that Bucky Fuller was connected to. And had we not been associated with his work, we probably wouldn't have made this discovery. So why don't we call it a Buckminster Fullerene, which is what they did. And then it's now shortened down to buckyballs.
Very cool.
Yeah,
I found the video,
good.
and it's only 2 minutes long. If I can get my machine to work, I'll turn on the volume. Oh, let's see. I forgot to, I have to turn on, well, come back here. I forgot to turn on the volume. Okay, here we go. You guys can see this now, right?
Yeah.
Yep.
Yeah, here we go.
What is graphite? Graphite is a two-dimensional sheet-like structure with each carbon atom bonded to 3 other carbon atoms via sigma bonds. Here, the carbon and graphite are sp2 hybridized. In graphite, each layer consists of planar hexagonal carbon-carbon cyclic structure. The 2 layers of graphite are held together by means of van der Waals forces of attraction and are separated by length equivalent to 3.35 angstroms. This separation between 2 layers in graphite makes graphite slippery in nature. The 4th electron of each carbon atom in graphite is free and moves freely between the layers. That is, the 4th electron is delocalized, which makes graphite act as good conductor of electricity. The 2p orbital of each carbon, having 2 single electrons, overlap with each other on sideway fashion and thereby forms a pi bond. Graphite is used as lubricant in pencil lead, electrodes, and acts as moderator in nuclear reactors. In nuclear reactors, the graphite slows down the speed of neutrons.
Very cool, eh?
Very cool.
So anyway, I just happened to
It's
see that,
interesting.
and here we are talking about it, and it's very exciting. At least we talked about it last week or something, or whenever the last time was we were on. All righty, so now we're going to go to Bucky. Any comments or anything before we proceed?
No, it's interesting. I just what are weak van der Waals versus I guess what would be the opposite?
You said what are weak what?
It's called van der Waals.
Yeah. I don't know. There's a weak force and a strong force, and I think it has something to do with that. If you want to do a Google search on it and see what happens
Yeah, that's
while we start. You're going to do a Google search? Let us know.
Yeah, right now.
Cool. All right. Shall we proceed while you're doing that Google search?
Yep, got it.
All right. I'll start to read. And here we go. 10 multiplication by chapter 10, multiplication by division in search of cosmic hierarchy. It may seem, I'll read for a little bit and then somebody else can read. It may seem that we have strayed from Fuller's operational mathematics while investigating the symmetrical properties of various polyhedra in the previous chapter. Recall that optional indicates, or operational indicates an emphasis on procedure and experience. What to do to develop and transform models or systems. Multiplication by division brings us back to experience, introducing an operational strategy, which will add new meaning to Fuller's term, intertransformabilities. We thus elaborate on the shared symmetries among shapes while discovering new transformations from one to the other, and this time previous experience allows us to anticipate results. If you find something, Joe, let us know, okay?
Oh, I did. I just put it in the chat.
Oh, you did? Well,
Yeah.
let's review that. You wanna, it's in Wikipedia.
Yeah. I was just looking at it right now.
All right, let's just share it together.
You want me to share it?
Yeah, well, I'm sharing it now.
Okay.
You want to read it?
Sure.
You want to conduct us through it?
In molecular physics and chemistry, the van der Waals force, sometimes van der Waals force, is a distance-dependent interaction between atoms or molecules. Unlike ionic or covalent bonds, these attractions do not result from a chemical electronic bond. They are comparatively weak and therefore more susceptible to disturbance. The van der Waals force quickly vanishes at longer distances between interacting molecules. Named after Dutch physicist Johannes Dietrich van der Waals, I hope I'm saying that correctly, the van der Waals force plays a fundamental role in fields as diverse as supramolecular chemistry, structural biology, polymer science, nanotechnology, surface science, condensed matter physics. It also underlies many properties of organic compounds and molecular solids, including soluble in polar and nonpolar media. If no other force is present, the distance between atoms at which the force becomes repulsive rather than attractive as the atoms approach one another is called the van der Waals contact distance. This phenomenon results from the mutual repulsion between the atoms and electron clouds. The van der Waals forces are usually described as a combination of the London dispersion forces between instantaneously induced dipoles and Debye forces between permanent dipoles and induced dipoles, and the Keesom force between permanent molecular dipoles whose rotational orientations are dynamically averaged over time. Okay. Personally, I'm going to need to digest that, but I'd also like an example.
Yeah, well, they
I
show
mean-
that there's the microfiber cloth makes use of the van der Waals force to remove dirt without scratching. And I did a
Yeah.
quick Google,
Yeah.
and I asked AI what the difference was between van der Waals force and the weak force. They're fundamentally different. Van der Waals forces are weak intermolecular forces, meaning they occur between molecules and arise from temporary or permanent dipoles. The weak force, on the other hand, is one of the fundamental forces of nature. It is an elementary force that acts at subatomic levels, specifically influencing radioactive decay and the interactions of certain subatomic particles. So my supposition was not the same. Rainwater flux from a canopy. Among the forces that govern drop formation, van der Waals force, surface tension, cohesion, and plateau-Rayleigh instability. Wow.
Now, this is interesting. Geckos can walk on walls and ceilings, even upside down, not because of glue or suction, but because of the van der Waals forces. Each
Is
toe
that
has
on this page or is this something else?
no, it's something else.
Okay.
Uh, um,
You want to share that?
yeah, sure. I'll just put it in the chat right now. It's just based off a chat. There we go. So geckos can walk on walls and ceilings, even upside down, not because of the glue on the suction, as I just read, but because of the van der Waals forces. Each toe has millions of tiny hairs called setae, and each hair splits into even tinier tips. Spatulae.
Spatula. Yeah, spatula. I remember that
Spatulae.
from my biology course.
Yeah, that's pretty good. These spatulae get extremely close to the wall with surface, just a few nanometers away. At that tiny distance, van der Waals forces, mainly London dispersion forces, kick in between the atoms of the gecko's foot and the atoms of the wall, even though the force between any single spatula. What's that? Spatula. That's what I could say, a spatula. And the wall is very weak. When millions of them act together, the effect is strong enough to hold up the gecko's body. That's interesting.
Cool beans. Yeah. Very
So I'm trying to
cool.
think now that how does that fit into the graphite example? And I'd really like to know why, and thinking about it in terms of, when there's some give in like graphite shafts in golf clubs, and it's interesting. And and I've played both irons and or steel shafts and graphite shafts, and the way they even absorb force, like absorb force, it's quite different. And I'm wondering how that actually factors in, because when I first see graphite, anytime I see graphite, I think about how it's used. That's where my first mind goes, and then I didn't know what the hell van der Waals force was. I clearly should have to some degree.
Well, and what's interesting for me, Joe, is that this uses van der Waals, what you just read about geckos, uses van der Waals force to keep the gecko stuck to the wall. And we're talking about van der Waals force in terms of making graphite slippery. So it seems absolutely opposite.
Yeah. Yeah. I mean, that's interesting.
Yeah, cool. Ready to read on?
Sure.
Okay.
Um,
You're going to read about geckos. You're going to, let me see. Let me start this page. Unless you want to read more about the geckos?
no, that's all I had, actually.
Okay, good. Multiplication by division describes Bucky's journey through our expanding polyhedral inventory. Previous exposure to both Loeb's work and the IBM set the stage, making us so familiar with these shapes that additional results can be immediately placed in context. The transformations explored in this chapter occur within the IBM frame of reference, adding volume relationships to our accumulated information about topology and symmetry. You may be surprised to find that many statements seem obvious at this point. Resist the temptation to dismiss them as trivial. Appreciate instead the implication, which is that we cannot take a wrong turn. Each step is inherently tied to the shape of space. We can only uncover what is already there. Any comments or questions? Seems to be pretty introductory. Volume. The use of ratio is an inherent part of quantifying volume. And Manu would be saying, of course, this is obvious. And yet not everyone is aware of the implicit comparison. As with measuring distance, our conventional units can seem like a priori aspects of volume. Once again, Fuller calls our attention to Avogadro's Avogadro's, whatever you say it, discovery that a given volume of any gas subject to identical conditions or temperature and pressure always contains the same number of molecules. A given volume of any gas always has the same number of molecules. Suddenly, we have our volume clearly identified with number, declares Bucky. Actually, volume is intrinsically related to number. When we ask what is the volume of the swimming pool, we expect an answer expressed in some number of cubic feet or gallons. What this answer tells us is how many cubes of an edge length of 1 foot could fit into a pool. Whether the situation calls for feet, inches, or centimeters, a cube or unit edge length is conventionally employed as 1 unit. The word volume may evoke an image of continuum. However, it is quantified in terms of discrete quanta. I hate it when they use the same word in the same sentence.
Yeah.
We also uniformly express spatial quantity in terms of cubes that are simply not aware of the invisible framework of ghost cubes. We so uniformly express spatial quantity in terms of cubes that we are simply not aware of the invisible framework of ghost cubes incorporated in our concept of volume. We conceptualize space cubically. Length, width, and depth seem absolutely fundamental directions. Again, Bucky points out that this conceptual cube is a remnant of flat earth thinking. Myopic is cosmic terms. Humanity readily adopted the orthogonal box as the correct shape with which to segment space. Okay.
That's a lot to take in.
Yeah, it is a lot to take in. I mean, how are ghost cubes incorporated in our concept of volume? I think of negative numbers as we try to figure out the square area of a surface or the cubic area of a cubic volume. The three-dimensional volume of a volume of a three-dimensional thing. Okay, I'll read. I don't know. I'm happy to switch off and let somebody else read. I haven't been here for a long time. Say what?
Yeah, I can go ahead and read. No worries.
Okay, I just feel like I ought to be doing some work. Go ahead.
Sure. Results volume ratios. Volume has to be measured relative to something. So why not experiment with the tetrahedron? We are so used to using the cube, the suggestion seems blasphemous, a violation of basic laws of volume. Nevertheless, given our growing list of tetrahedrons' unique properties, such an experiment might be worthwhile. Accordingly, we allow a tetrahedron of unit edge length to be called 1 unit of volume. The results are astonishingly rewarding. Perfect whole number values describe the volumes of most of the polyhedra covered so far, and all of the contained within the IVM and IVM combined. Some exceptions are found in transition shapes, those that fall in between the IVM vertices, as we shall see in the next chapter. In contrast, the volumes of these familiar polyhedra relative to a cube as the unit shape are strangely cumbersome values, often irrational, never-ending decimal fractions. Table 10-1 displays the results, which we shall derive below. It compares the volume ratios generated by the 3 different polyhedra successfully adopted as 1 unit of volume. 5 different systems are compared, first with the unit edge cube, then with the unit diagonal cube, and finally with the unit edge tetrahedron.
So let's see what 10.1 shows us.
There we go. All right, so we have the polyhedron measured, the tetrahedron unit edge, the unit diagonal, and the unit edge.
So it looks like we get a bunch of irrational numbers on unit edges, where if we simply use a tetrahedron, we have whole numbers everywhere we go.
Correct.
Cool.
That is interesting. That's the octahedron's one. Okay. Well, for
This is the
cube.
vector equilibrium, which is the cube octahedron.
Right. And that's 2.3 and 6 to 20. That's interesting. When you think about edges from that perspective.
Yeah.
And I'm trying to think about how that would work with in just terms of graphs. That's kind of where my mind's going initially when I start thinking about that. How, the edges and the nodes are connected, obviously. And I mean, these are shapes that they're connecting, but then what are those shapes representing? And I think about that in terms of kind of knowledge graphs, I should say.
Cool.
And I don't know if there's a direct correlation, but I'd have to think about that for a little bit longer.
Shall we continue to read?
Sure. Remember that these polyhedra arose as a consequential of spatial symmetry. We simply located vertices within the unique isometric array of vectors. Recalling this origin, it is again clear that the various shapes and sizes of the polyhedra in question are not the product of deliberate design. Their whole number volume ratios are not contrived. We stumble onto them after the fact. While we investigate 2 different cubes, primarily to demonstrate that neither choice yields the elegant results disclosed by the tetrahedron. All factors considered, the unit diagonal cube is a better choice, for it arises naturally out of the IVM network. That is, out of the shape of space. Further justification of this choice will be developed below. Imagine building a cube out of the requisite 12 struts. The topological recipe, which simply calls for 3 valiant vertices and 4 valiant faces, in no way indicates precisely what the finished product should look like. Without deliberate shaping into a perpendicular form by a knowing hand, the configuration does not favor any particular surface angles. Which version of this hexagon of quadrilaterals is the desired result? The ambiguity must somehow be resolved. Chapter 5 revealed that an orthogonal cube, as defined by mathematics, cannot be reliably created without diagonal braces. Refer back to figure 5-3. Compare this experience with building an octahedron out of the same 12 struts, following the recipe of 4 valiant vertices and 3 valiant faces. The octahedron builds itself. The interior shape is precisely specified by its topology. In other words, the procedure leaves no room for choice. In order for the cube to have that kind of integrity or exactitude, 6 face diagonals must be inserted. An inscribed tetrahedron solves the problem in a single step. The above comparison reinforces our previous experience of how the right-angled cube fits into spatial symmetry. Fuller's operational mathematics prescribes learning by procedure. Pick up a box of toothpicks, pre-cut unit vector models, and start building. Space will let you know what works. That's interesting. The satisfaction gained from the feeling of the cube, from feeling the cube hold its shape draws attention to its supporting diagonal members, and thus unit vector diagonals seem an appropriate choice for comparing volumes, as volume is always a matter of ratio. We want to ensure that our comparisons make sense. In this case, remain constant with space's isotropic vector matrix, that the vector matrix diagonal cube is contained within this hierarchy adds to the advantage established by its stability. Any comments or,
I understood some of that.
Me too. I mean, it's interesting, the idea how, trying to think of how the space will let you know what works.
Yeah. Well, and that's it. If I build a cube, it'll fall over unless I put diagonal braces in it. The space is letting me know what works. What works is the diagonal braces in the cube, and if I don't have diagonal braces in the cube, my cube is not going to make a house.
Well, it's interesting because, and this is where I just break into some of the philosophical aspects of it. And, that I think it's like, I want to say it's the Tao number 12, when they talk about how the space makes the wheel, and how the empty space makes the room. And it's essentially how the space actually creates the object.
Isn't it the same to say how form follows function?
Correct. And
Yeah.
so hang on. We've brought this up, and I've mentioned this in the past, but it's just worth mentioning again. It's chapter 11, not 12. Yeah, anyway, it's not to go into detail here, but it's interesting. This is where some of the ideas that just philosophy actually does somehow provide the basis for analytical rigor to be applied. That's all.
It's for me, it's very profound to ponder the fact
Me too.
that a cube falls down and a tetrahedron doesn't.
Right.
And to say that the reason why that happens is because the shape of space is profound. I would say that the reason why the tetrahedron doesn't fall over is because everything's leaning on itself. And the reason why the cube doesn't fall over is because things aren't leaning on itself. There's, 12 independent, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 different vertices in a cube, and none of them are leaning on each other, so they fall flat.
Yeah, it becomes the tetrahedron becomes self-reinforcing in a way.
Yeah. And it's
And-
interesting that the Native Americans built their teepees based on a tetrahedron.
Yeah,
They
that's right.
put 3 poles up. And then once they have those 3 poles up, then they put other poles around that are not quite the shape of a tetrahedron, but they make the tetrahedron spherical. So there are 13 poles in a teepee. The 3 main poles and then 5 around this side and 5 around that side.
No, I think there's 15.
Is there 15?
Yeah, 3 and 4 in between. 4 times 3 is 12 plus 3. And
So
it gives us then the circular base, yeah.
Let me think about that.
I just did a quick Google asking how many the typical teepee has between 12 and 25 poles. The exact number depends on the size of the teepee.
Hmm.
So they
What
don't
does it
know
say?
anything.
12 and 25.
It does, it says 12 to 25. So that would be the 3. See, this is caca because you have the 3 that built. No Native American starts without a tetrahedron, and they aren't equally spaced. They take 2 of them and face the east or west or south or north, depending on the tradition and the tribe. They take the 2 and then they lean those 2 against a third one, and it makes it an irregular tetrahedron. And then the other poles go around each side. So I would have said 13. 15 works for me, Richard, because that puts 6 around each side instead of 5 around each side. So I think that a bunch of heathens built the Google post.
Yeah.
So those people don't know nothing. They didn't read Blackfoot physics. They didn't read that book. Okay, cool. Any other comments or
It's
questions?
interesting. No, I mean, I just think again, this is an interesting thing where essentially Amy, I mean, she talked about in the beginning of the book how she built all these things and was exploring these ideas, but she was even talking this is the same thing as when she talks about Fuller's operational mathematics prescribes learning by procedure. Pick up a box of toothpicks, pre-cut vector models, and start building. And the space will let you know it works. The satisfaction gained from feeling the cube hold its shape draws attention to its supporting diagonal members and thus
Did you
unit
start
vector
reading again?
diagonals. No, no,
You-
well, yeah, I am reading it. It was, but it
Oh,
was,
you're reading this down here?
I was reading the same thing I just read.
Oh,
No,
you're
I wasn't.
rereading what you read?
Yeah, it was just that's an interesting section, I think.
Me too.
I really do.
If I ponder and say, if I'm a normal person, I say, okay, the reason why a tetrahedron, if I take 3 poles, stick them on the ground, gravity holds them together. If I
Right.
take 1, 2, 3, 4, 5, 6, 7, 8 and try to build a house, gravity makes them fall apart. Now, and therefore she is saying that the reason why the tetrahedron holds its shape and the cube doesn't is because of the shape of space. So let's turn that around. If space were shaped in the form of a cube, then the tetrahedron would fall over. If
Right.
space were in the shape of a cube, if I put 3 things together, they would not have a shape. They would fall over. And when I think of that, that really blows my mind. You
Well,
know,
I mean, I think in terms of systems, how that's kind of like, uh, it's almost like a regenerative system in a way. It relies on itself
mm-hmm.
in a way.
And it relies on itself because it's the shape of space. I mean, that's
Correct.
the point she's paying out here. The reason why it works is because that's the way space is shaped.
Mm-hmm.
That's just a whole weird concept for me. The
It
shape
is
of
weird,
space.
but it's
Yeah.
cool.
Who ever
There's a
thought
weird
of
way of
space having a shape? But you know
Yeah,
what?
exactly. No,
But you know what?
go
Go
ahead.
ahead. Go ahead,
No,
please.
no. No, I mean, no, when you think about it in that term, in those terms, actually things do start to kind of make sense. It's the wording that kind of, you know, the wording throws me off, but it does make a lot of sense as far as how, the shape of space and how that relates to the object
Yeah.
and how that actually kind of allows you to understand the structure itself.
Yeah. And that's the reason why in the Tao it would say that the wheel is conforming to the shape of space, right?
Yeah, I mean, it says that, the 30 spokes share the hub of a wheel, yet it is the center that makes it useful.
Yeah, the center of the hub. Now,
Yeah.
this means that if
Hmm.
space were shaped in the form of a cube, the wheel wouldn't work
Right.
because it'd have to be a cube.
Well, and the interesting thing is, cut doors and windows from the walls of a house, but the ultimate use of the house will depend on the part where nothing exists.
Yeah,
Therefore, something is shaped what it is, but its usefulness comes from what it's not.
yeah. All these words are in the chat. So if you're listening to the video and you want to know, grab that chat, and you'll see Joe's comment there around 10:03 p.m. Yeah.
Yeah,
And
that's what.
interestingly, I have a new video that I have not yet watched because I haven't had time, but it's talking about how in the Hadron Collider in CERN, they put all the data into a large language model AI, and the large language model AI identified a pattern that existed below the particle.
Hmm.
I haven't listened to the whole thing yet, but I think if that is the case, then we are at the Hadron Collider. The AI identified uh, something underneath that had to do with AI Hadron Collider and a new form.
I would like
It
to see
actually
that.
describes a new pattern or a new form. What's that, Joe?
I'd like to see that. Uh, it's just really quickly, and I mean, so I, just out of curiosity, I put that down to uh into chat, and then and it's interesting how it sees it relating both to the tetrahedron as well as to quantum field theory. And this is something that there's a presentation on this about 52 living ideas, essentially. Oh, great. Over by 50 words. Hang on 1 second.
Oh my gosh. Now I've got a whole thing here. Quantum AI just translated the Tibetan Book of the Dead and discovered something about physics. My gosh,
Yeah,
what is AI going to do?
yeah, it really is. It's pretty remarkable. But yeah, I mean, it says, field theory, and hang on, it even talks about its relationship to Bucky. So this is something obviously that Richard would be interested in. 1 second.
What did you decide?
No, it's something that Richard would be interested in. So the Tao, actually, in comparing it to Bucky's ideas,
Oh yeah.
And it relates tensegrity and emptiness as structure. And it's, Buckminster Fuller's tensegrity structures, tensional integrity, uses compression and tension elements arranged so that the actual material is minimal, yet the structure integrity comes from how the space is organized. Like the clay vessel in the dowel, it's the void between the struts that allows the system to exist and flex without collapse. Geodesic domes are not solid. They enclose space using minimal structure. Their strength comes not from mass, but from the arrangement of empty space using triangles and polyhedra. Another echo of usefulness from what is not. The tetrahedron is fundamental unit. Fuller championed the tetrahedron as the most basic stable unit, three-dimensional, we all know that. The tetrahedron encloses space using the fewest vertices, edges, and faces, emphasizing the geometric stability arises from efficient enclosure of emptiness.
Yeah, what's interesting for me, and I was just doing some stick figure drawings here. If I had thinking about building a teepee or building a structure, but if I had a pile of poles laying down beside me, and my intuition was that I needed to build it with right angles. So I'd take probably 2 poles and stand them upright. And then I would take a third pole and maybe put it across the top, and it should be freestanding, but it is not. It falls over. So then I continue at the top, and I put another pole, and then another pole, and another pole. So now I've created a square, and I drop a pole vertically on the other 3 corners. So now I've got 8 poles, and 4 of them kind of like tent legs, and now it should stand up, but it doesn't. Then I go back and I start all over again, and I pick up 2 poles, and I sort of angle them together, and then I pick up a third pole, because those 2 poles will fall over. And then I pick up a third pole and I put it in another angular form. And all of a sudden I discover that I've actually created 3 triangles, faces, and the damn thing holds. And I haven't put anything on the ground yet.
Do you have that drawn out? You have that drawn out?
Well, I just sketched it, yeah. But I don't have it in the way that Manu might have drawn it out. But
do you have it in the way that just explained it, or?
Yeah. I mean, I don't know whether I can get it up there close enough so you can see it. But on the top there, not at the real top, but where you can see the cube structure, I've got 8 poles, 4 going upright and 4 across the top. And the 4 upright are just sort of sticking in the ground, but they won't hold. But if I then go back and start over again, and I use 2, which falls over, then I take the third and lean it against them. I create three triangular faces. I haven't put anything on the bottom, just like the other one doesn't have anything on the bottom either. And yet my triangular faced one actually holds, because, as you said before, the way the poles are angled, they form a bottom triangle that contains it.
Right.
It acts like it stops the radiation of the leg.
Sure.
Right.
Whereas the other one doesn't.
In a sense, what happens there is that we say, oh, well, the reason why the three hang together is because of gravity and they're leaning on each other.
Right.
But the idea is that the vector equilibrium, the isotropic vector matrix, is made of these triangular radials with sometimes squares, and that's what creates the gravity. It's not because gravity is affecting, it's because the shape of space creates gravity.
Right.
Exactly. Exactly. That's well said.
Yeah.
And it's
Wow.
again, it's a little bit like Fuller saying, if you draw something and a convex of something, you've automatically drawn the convex. The concave, if you do a concave, you've already constructed the convex. In the same way here, if you upright three triangle faces, even without trying, you've created the fourth triangle face on the bottom.
Yeah.
And and because of
Because
the
that's the
angle,
shape of space.
yeah,
We could
uh,
say because they planted on Earth, but Earth wouldn't be there if it weren't for the shape of space.
mhm,
Oh, this is blowing my mind.
Yeah, I know.
And I found that video of the AI talking about a new pattern. If
mm,
you're ready, I'll share that.
okay,
Interested? All right, here we go. Um, it's elusive, but nonetheless, I'm going to start 1449, and it hits the word pattern down here. But let's see what it actually says here. Okay, go.
Though it remains hotly debated, none of these ideas are conclusively proven, but some fit nicely into frameworks that predict new phenomena at high energies. CERN scientists, when searching for new physics, sometimes look for small anomalies that don't line up with the standard model. If they find consistent patterns in these anomalies, it might suggest something unexpected, a new particle, an unknown force, or even an interaction hinting at a parallel dimension. Historically, a few anomalies have popped up, stirred excitement, and then gone away as more data was collected. That's part of the normal process in a big experiment. Still, the chase continues. Speculation.
Okay, so here's the words over here. The particle is an unknown force or even an interaction hinting a parallel dimension. Historically, a few anomalies have popped up. So it's a patterns. These patterns are different than the standard model, and these anomalies suggest something unexpected, a new particle, an unknown force, or even an interaction, hinting a parallel dimension. That's the isotropic vector matrix.
Yeah, can you put that actually in the chat? That is
Yes, I
exactly the
can.
IBM. That's actually the best example of the IBM I've seen.
Yeah, and this guy doesn't know what he's talking about, and yet, in
yeah,
terms of sacred geometry, right? I'm going to
Just put
put
the you can put the link in, or you can put the
I'm going to
word
put
in
the
as
link
well.
in too, but I think that it's fun to have this parallel universe thing in here.
Yeah, I agree.
So let me I'll find the chat. There we go. I didn't I listened to it and I thought, oh boy, this is this BS thing. You know, um why are they the guy doesn't understand what he's saying, you know, they're struggling with it. It just boggles my mind. So okay, there is the little part that talks about the unknown particles. And then here is the link. Bonk. And I'll have time to listen to it. It mentions the patterns a couple of times, but it's like if he'd read this chapter before he started writing this video, he might have said something else, right?
mm, yeah.
Wow. Okay, shall we go back to read more or do we want to discuss more?
Well, just one other thing that just my own personal experience, which I may have already used this example at some other time, but um, when I had a a tetrahedron structure. Um, this one, the tensegritoy that has the elastic sort of holding the struts together. And I was trying to explain the tetrahedron, to a group of child welfare workers, some of which were indigenous and some were not. And using that model, produced a number of glazed looking eyes. But when we were out for lunch, one of the indigenous child welfare workers came to me, whispered in my ear, and said, I get it. That's how we think. And so it was, I didn't catch that sort of nuance when when it happened. But even today, when you look at what we just discussed, it was like she said, we think like a teepee is built.
Yeah.
And everybody else was probably confused because it didn't have these perpendicular kinds of poles or angles in it that
Right.
they would have normally thought should be there.
And so, Richard, hold up your tensegrity example again. So, in this context, reality is not the sticks which I see, it's the elastic that holds them together. That's
Yeah,
the reality. And what you're saying is your Native American person thinks in terms of that tension, not in terms of the sticks.
right.
All right.
Where white folks think about the sticks and
And
we
not,
put in nails and braces to create the tensegrity
yes,
without thinking about it.
yeah,
Well, and
exactly.
one's about focus more importantly on the relationships
Yeah, on the
between the state.
interrelationships.
Yeah, and that's that
And
versus the other
then the
one's
other thing, it
actually
was just even today,
focused
I
on.
was looking up something more again, and I ended up with the root words of tensegrity, and it was the tensile, the words that Joel read just a little while ago, tensile and integrity, and he combined them into tensegrity. But what I've been trying to capture in my own mind is that, again, it's not one of these either or, it's compression or the tension. It's both and. And what it was telling me in words that I made more sense than other words I've read is that between the two of them, the compression and the tension, um, they allow the offloading of one to the other, or the reverse. So if, again, I'm thinking in a social context, so if I'm feeling overwhelmed, if I am being weighed down um, by the compression of all the things that are happening to me, if I'm connected to something else, I can offload that pressure through the tension onto somebody else, which might be a support person and that sort of thing. But likewise, if the tension between my relationship with somebody else is getting to be too stretched or too much in my face, you can offload the tension onto one of the compression elements. In other words, somebody sort of sucks it up and says, okay, let's just agree to be disagree type of thing. But they take on the burden of the tensional um, stretch in a way that they can handle it. It's not too much for them. And so there's this constant exchange between the compression and the tension of offloading on each other in order to stabilize the overall system, or to keep it in this dynamic equilibrium that we often talk about. And I did not capture in my own mind up until today this idea of it being reciprocal, back and forth offloading.
Yeah.
And
Yeah,
Are you complete, Richard?
yeah,
Okay, good.
yeah, for me, and I brought this up a little bit on Wednesday as well. What these relationships enable is where you start to see what Bucky's ideas came, or where he had come to the ideas like ephemeralization. Because these are the efficient uses of resources when you're doing more with less. And so when you think about it from that perspective, it becomes a little bit more, this is how it becomes like almost an economic model as well. So it's the efficient use of energy, and that's what actually even Amy's been going through since she had the 12 and 13 cookies, is the efficient use of space and the efficient use of kind of materials. It's you could start to see how he had come to that conclusion, and it also leads to other ideas as to how to even work with the existing structures, like and have an idea like the trim tab. So once you understand the structures themselves, the way we do, and the way this is being described, well, obviously, you know how to use energy efficiently so that you can actually use something like the trim tab, to redirect a ship and use it to use its energy much more efficiently just by using
And so, are you complete, Richard? Are you
yeah,
complete?
yeah.
Okay, good. So, Richard, unwittingly or wittingly, you actually corrected me, because what I said was that they don't think in terms of the sticks, they think in terms of the tension between the sticks. But you said correctly, they consider both.
mhm,
And I think so I'm changing what I said. I'm going to now say they don't think in terms of the sticks. They think in terms of the sticks and the tensions.
right.
And this comes back to what we were talking about on Wednesday. It's the great mystery, because they acknowledge the great mystery. And Joe, to your point about trim tabs, we might be able to do some irrational number calculation, differential calculation on why a trim tab works, or we could just admit it works because it's the shape of space.
Mm-hmm.
Gravity is because of the shape of space. It's not that gravity is a force. In fact, nobody can find gravity. They're trying to find gravity waves. They can't find gravity waves. They've now measured they think they've got some gravity waves from the beginning of the Big Bang, but then they find out the Big Bang is before they thought it was. So they're looking for quantum gravity, and they can't find quantum gravity. It's because gravity is an artifact of the isotropic vector matrix. The reason why the trim tab works is not because of some irrational number differential calculation about water streaming off of a little thing. It's because that's the shape of space. And that trim tab just uses the space properly. Well, this whole thing about the shape of space is blowing my mind. I'm trying to rewrite everything in my brain saying, oh, because of the shape of space. Why do we have a strong force and a weak force? Because of the shape of space.
Yeah, that's exactly right. That's absolutely right.
Whoa.
Yeah, I know, when you think of it in those terms, that's where you start to be able to understand that.
Yeah. Whoa. Totally amazing. Joe puts in the chat force-based models to shape-based models. Ooh, yeah. Loop quantum gravity and other theories explore how space itself has a discrete geometric structure, which is what that video alludes to without being aware that it's alluding to it.
Yeah.
Right? Because it says, well, it discovered some pattern. Is it a new particle? Trying to consist in the old model. Well, if you ask Donald Hoffman, it's the amplituhedron, which is, I think, Donald Hoffman's way not to say the isotropic vector matrix, because
Yeah, right.
as soon as he says that, he's into sacred geometry. So by saying amplituhedron, staying scientific and non-committal. Anyway, interesting. Cool. Shall we proceed?
Sure.
There's a neat graphic here, if we get to it. Oh, I don't mind reading for another minute. Richard, do you want to read?
No, go ahead. I can come
Okay.
in a little bit.
Shape comparisons, qualities of space. Once again, we take advantage of the ease of working with planar configurations before tackling space. We thus start by comparing the characteristic of triangles and quadrilaterals, and then we attempt to apply our conclusions to tetra and cubes, which is what you've been doing with your pictures, what we've been talking about. So we're right on course here. We begin by drawing an irregular version of each polyhedron and observe the following. If we bisect the edges of two figures and interconnect these points as shown in figure 10.1a, both shapes are divided into 4 regions. However, the triangle and the quadrilateral exhibit a strikingly different result. Let's take a look at that just briefly.
Mm-hmm.
There's your triangle. You keep getting more triangles. Interestingly, a triangle, no matter how irregular, automatically subdivides into 4 identical triangles. Woo! All geometrically similar to its original. That is the same shape, but a different size. Of course, this comes back to the shape of space when you start chopping things up. Observe in figure 110a that this is not true for the quadrilateral. Excluding the special case of a parallelogram, the 4 small quadrilaterals will not be similar to their framing shape. In other words, if it were a square instead of a trapezoid or whatever this thing is here, if it were a square, it'd have similar. But if it's not a square, then it's going to be nothing's the same. Whereas if you take an irregular triangle and you clump it up, you have multiple triangles the same shape as the irregular triangle from which it sprang.
Right.
Ditto with we haven't talked about B yet, but here's A. Any other comments or questions?
Well, that diagram for me is getting at the heart of multiplication by division. So as you say, if I go to the triangle and I divide at the midpoint, so I turn one triangle into 4 triangles, it's going to take on the shape of the triangle, whether it's equilateral or not. And then, as you say, on the other side, if I start to divide at midpoints in the square one or the rectangular one,
the irregular rectangle, yeah.
The shape is going to change,
right.
And they're not going to be identical.
And they're not. This creates fractals, and
yes,
this does not create fractals.
right. And this is the
Whoa.
whole point that Bucky was getting at in the book that he did with kids, in trying to show people the difference between the square times table and the
Cube.
triangle times tables.
Yeah.
And showing that you get the same answer. In other words, 2 by 2 is 4. But when you also see that it takes up far more edges for the rectangular one than it does the triangle, and it takes up more area, more space. And so that's why Bucky ended up saying nature multiplies, if you want, in triangles, and man multiplies in squares. They get the same answer, but nature just happens to be more efficient and more conserving of space than man is.
Yeah.
And And he demonstrated it by showing the square times tables in the form that we just see it there, and the triangle times tables. Kind of interesting.
And I'm going to reiterate for me, the big point is, Mono's coming in. The big point is that when I take this even irregular triangle and I dissect it by drawing a character that's midpoint between these things, I create a fractal. I create the same
Yes.
shape. Where if I take this irregular square and I cut it up by creating intersecting lines at the midpoints, I'm actually creating, I now have 5 different shapes.
Mm-hmm.
None of these shapes are exactly the same as the shape from which it came. I can't measure them. I'm just guessing that from what we've done over here. Manu, how are you feeling? Cool.
Well, right, sir. Thank you.
So let's finish that last paragraph. Maybe we did, but I'm going to read it again. A triangle, no matter how irregular, automatically subdivides into 4 identical triangles, all geometrically similar to the original. That is, the same shape, but a different size. That's the definition of a fractal. Observe in figure 10.1a that this is not true of the quadrilateral. Excluding the special case of a parallelogram, so she's saying any kind of a square, it can be an array, it doesn't have to be it can be a parallelogram. So the 4 small quadrilaterals will not be similar, except in that one case. Now, on to space. A tetrahedron of any shape or size, carved out or firm cheese, can be sliced parallel to one of its faces, removing a slab of any thickness to produce a new smaller tetrahedron with precisely the same shape as the original figure. See 10b.
Mm-hmm.
10.1b. This does not work with the cube, or for that matter, with any other polyhedron, regular or not. The ability to accumulate asymmetrical aberration without altering shape, observes Fuller, is unique to the minimum system of universe. We add this observation to a growing list of special properties of the tetrahedron. See Appendix C. Similarly, as well as will be demonstrated below, an irregular tetrahedron can be subdivided to create smaller identical tetrahedral shapes, whereas an irregular hexahedron will yield dissimilar hexahedra in the same manner as a planar counterpart, the quadrilateral. I looked ahead, and there's no picture showing that. Evidence thus gradually accumulates to support using tetrahedron instead of cube as the basic unit of structure of mathematical starting point. Cool. And we're getting close enough to the end that this is probably a good time to go. And Manu, you have your hand up. So what are you noticing about this? Or what do
Just
you
one
want to
point.
say? What
No,
one?
I just wanted to say something.
Yeah.
I always, at the risk of annoying you guys, going back to the fundamentals. The fundamental is this one. On a plane, a triangle is irreducible. It cannot shake. It is solid. A triangle of any size is a solid shape. A square or a rectangle is always shaking, is always flexible. Those are the 2 fundamental duals of motion of energy in universe. You take a triangle to make the struts, and you take a square or a rectangle to shape. That is to imprint the vibration, to imprint the contracting and expanding, contracting, expanding. It is fundamental to me. with that in mind, I got into this thing right at the end, and I'm not beside the discussion. I think that I'm flowing the discussion, hearing the few words I heard from you guys. That's all I had to say.
Cool. Well, we talked all about what you just said. We've been talking
Yeah.
about it the whole night.
Not as
Okay.
eloquently.
So you had the benefit of it without reading all this stuff. In fact, we even said that in the recording. I even said that in the recording. Okay, so we're gonna wrap it
But
up.
adding that is advantage of somebody like anybody that is in this forum has in terms of education from the commoner.
Yeah.
There are basics that you get that allow you to jump onto the fractal
Right.
without the complicated maze of things that are irrelevant. That is, to me, the main benefit of the whole time that you spend studying Fuller.
I tell you, you should write a book, Manuel, on fundamentals. I'm not kidding.
I am,
Oh, good.
yes.
Cool.
I have
Can I
notes.
get an
I have
advance copy?
notes. I have notes.
Cool. So it's time to
Yeah, like, okay, just go on and then I will share what I wanted to say. That's what, yeah.
okay, well, we're gonna wrap it up right now. So Manu, how are you feeling and what do you got to say? And pass it on when you're done.
I feel ashamed of sleeping too much, but I had to sleep. I was really tired. I remember my spouse saying, go and do this, go and change, go and put on your pajamas. I said, yes, I will do. I did that at 2 o'clock this morning. And I came back, I slept again. You know, I was aware at 3:30 that I ought to be up at 5 o'clock. I couldn't. I just went to sleep. Anyway, that is good for me. Maybe it's bad for my friend, but it's good for me. What I want to say is, if we understand the principles, we understand that it just takes two derivations, that is two cutting in the middle, to describe the whole structural universe. Two cutting in the middle. The first yield 4 tetrahedra and 1 octahedron. The second yield 8 structure. So that is, to me, that is, no, the second yield 12. And that is, to me, a fundamental. Another thing that I take is what I put last time we were discussing, which is I want you guys to maybe help into that, into generalizing it. That is, that we had three constituents of universe. They were the boundary of universe, they were the vector equilibrium, and they were the domain. And I posit that generalizing Euler's identity, the vector equilibrium plus the domain minus the boundary, reducing the space to the two, which is the two poles of a system. Every system is going somewhere. There's no system that is there permanently. So if you're going somewhere, it is a vector. That vector has, let me call it the South Pole in reference to our Earth, and the North Pole. The South and the North is going somewhere electromagnetically. So vector equilibrium plus domain minus the boundary. Boundary to me is the outer edge of flow of energy in the system. It's like if you take our skin off and you look at what we have, it's like the edges of of a polyhedron, of a tetrahedron. It's also like, you remember that Euler's relationship is vertices plus faces, faces being the domain, representing a domain on a smaller system, minus the edges. The edges being here, the boundary, is this out of a polyhedron equal to. That's what I pose it to you. And otherwise, to the Americans, happy Independence Day. It means a lot to the world.
Cool.
The 14th, the 4th of July and the 14th of July. So otherwise, it's good. I feel good and I'm starting my day good. Joe, I see that you are basking from, coming from Greece.
Greece.
Coming,
Yeah.
nice time. How do you feel about your takeaway?
You know, it was interesting because I really did mean it actually. You know, there's a couple times that, you know, everybody's, you know, kind of spoken in here, and they've been on point with any AI that I've used. So, and Steve has actually did that tonight. And Mimino has done it in the past as well. But you know, for me, there was a couple, I mean, there was a lot of interesting things that actually had come out tonight. And I mean, obviously relating it back down to aspects of the DAO. But even looking at it, you know, from the perspective of force-based models versus shape-based models, and kind of seeing it through that lens, and not totally dissimilar to something that I've been working on, as I mentioned here in the past, and I shared a couple of things with Steve about this idea of like this essentially a language that's based on shapes and colors, and how words kind of represent more of the force-based model. You know, you say something and it's more about you know, how you say it, how emphatically you say it. And it's also has there's certain connotations that come with it that pervert people's thinking. But a shape-based model, there's more of a gradient, and the communication becomes actually much more nuanced, I guess is the only way to say it. Or as my friend would say, you know, it's more of a tensor, not a scalar, whereas the words are more of a scalar. And when you look at it from that perspective, you know, that's an interesting way of looking at the dynamics of actually communication. The bottom line is that it's more about the relationship between the objects and how that relays information versus how words relate to relay information. And I just think that that's actually very close to the idea of force-based models versus shape-based models, in my opinion. That's just a thought that I had, an insight that I had as we were going through this. And I thought it was really, you know, really an interesting conversation on a number of levels. Obviously thinking about things in terms of the space in between things and how that creates the object. You know, we've talked about that in the past, but just the way it was framed tonight, instead of thinking about it in terms of gravity, you know, we're thinking about how, in other words, how the space actually creates the object. And so anyway, I thought this was this is an interesting thing, evening, and appreciated your contributions at the end, Manu. So yeah, I don't know if Lee's still here.
Lee, if you're well enough to share, you can unmute and go for it. If you're not, we'll skip you and allow you to rest.
Well, I hope she feels better, and then another thing really quickly is I've just been thinking about Kelly. I don't know if anybody's spoken to him, but I did think about him earlier today, and I thought about him this evening. So I remember he had a pretty good command of these topics. He could always, kind of bring us back whenever we needed to, and not that we need to, but it was just just something to think about. So Richard, how do you feel, and what are you taking away from today?
Well, oh, I feel good. Been looking forward to the discussion when we get into multiplication by dividing. It's always been fascinating for me when I first understood it. And just to connect a little bit with what Manu was just saying in terms of Happy Independence Day, I started off this evening talking about another colleague that's on this World Weavers Zoom call every other week, and he writes sort of mythology or mythological sort of poetry, prose poetry, and he posted something the other day saying that independence is an illusion, and I followed up on it by saying, and interdependence is all there is. And then we had a little bit of discussion around independence days, and that I'm hoping that that in countries that put a lot of stock in this whole idea of independence, that one day that they'll realize that they should be celebrating Interdependence Day and promoting it. And so if I can take off on Manu saying Happy Independence Day yesterday, I would say Happy Illusion Day yesterday.
Wow.
But yeah, but the other thing in terms of the multiplying by dividing, it really intrigued me when I first understood how to take a triangle and divide it in the midpoint, and I would have 4 triangles. And I had this idea of the minimum whole. And then in my work, I was trying to figure out a way, how can I take a contextual, systemic sort of part of the tetrahedron and combine it with a procedural or methodological part. And so I finally was able to do it by a second level of midpoint division, so that I ended up with the 1 triangle to 4 triangles, and then I went from 4 to 16 triangles. And I was then able to take 3 of the triangles times 4 and rearrange them so they had one sort of with its point down, one with a point up, and another one with a point inside the second one. And those are the 3 contextual ones. And then I was able to take the top triangle and fold it in a way that I ended up with either 3 phases or 4 phases. And then I could connect them together through some pathways. And I ended up with one of these both and kind of models, both systemic and systematic, or both contextual and procedural or methodological. And I could never have done it with anything other than the triangle and understanding multiplication by division. Um, and so I've been ever grateful for understanding the triangle as Manu just described it, and then to see it transform, if you want, into a minimum whole system, the tetrahedron, and then seeing how you multiply by dividing in that fractal sense. But I went 2 layers to get the basic framework, if you want, for this combined contextual procedural model, and then applied it into my discipline. So this has always been an exciting sort of part of either reading Fuller or reading Amy Edmondson after I got to meet her in 1995. So that's how I'm feeling it now. Are we back over to you, Steve, or is it to
Yeah.
Manu?
Yeah. And so thank you. I kind of am reading ahead here and reminding, but of the role of the octahedron relative to dissecting a tetrahedron at the midpoints. And if we remember, the isotropic vector matrix is made of tetrahedron and octahedron. But what I wanted to get tonight is this profound epiphany about the shape of space. I've said it several times, but it seems to me that the big revelation for me is if I take a triangle, any irregular shaped triangle, I dissect each of the edges at halfway, I create 4 of exactly the same irregular triangle. It fractalates. If I take other than a square, if I take any kind of a rectangular shape that's irregular, and I divide it and I cut it in half, I'm going to end up with 5 different shapes. They're not fractalated at all. Now, and then, so that that is a powerful thing. I hadn't thought of that before. And then I'm thinking about this idea that going back to that chart about how when we start looking at edges and looking at sides, if we measure things in terms of an octahedron or a tetrahedron, we get whole values, whole numbers all the way down the line. And if we do any other kind of measurement, we end up with irrational numbers all the way around, describing relationships of cubes and things like that. And then we go to thanks to that video I shared about the Hadron Collider. No wonder the Hadron Collider keeps discovering new particles. Because when you take a energy, and if you take a force and you break it up, it creates irregular shapes. It doesn't fractalate. I mean, because they're looking in the wrong place. And so I just say, well, you take a square, you cut it up, you get 5 different shapes. You take an electron and you shoot it through the Hadron Collider, and you get all sorts of crap. And so nothing's shaped, nothing's conformed, nothing's fractaled, and so quantum physics just spins out of control. And now that's the reason why people are no longer looking at quantum physics like a solution of the problem. And maybe this LLM model that I showed, maybe that by revealing that pattern underneath, maybe we're actually getting some scientific indication that there is an isotropic vector matrix. And like I mentioned before with Donald Hoffman talking about an amplituhedron in order to avoid Bucky and avoid sacred geometry. So I love this idea of chopping up an irregular square and having 5 different shapes. That just blows my mind. I love the idea of saying a TP hangs together, not because of gravity, but because that's the shape of space. And a cube falls over, not because of gravity, but because it does not conform to the shape of space. I'm going to sleep on that tonight. I'm excited about it. Okay, good. And it's 11:02. Yo.
Can I borrow 2 of your minutes?
Okay, we're 2 minutes past our time,
Since
but go ahead.
I was late and my nav layer here today, so I can borrow, right? Okay.
You what?
An out layer tonight. Out
Okay.
layer. Yes.
Okay.
Okay. let's just think about if the relationship that I gave at the beginning there, the general Euler relationship holds. Can we give a thought to what the significance of two, the number two? And let me give you what I think is. Two is a signature to say that universe is pulsating. If you write that relationship like Kelly used to write, you see minus boundary. The minus is gravity, right? To Kelly. Minus men coming in. You remember that?
Mhm.
So you have minus boundary, then plus vector equilibrium plus domain, it gives you a symbol, two. And if you interpret two as a symbol in Kelly's writing, what is the symbol? What does that symbol mean? That two, of which one end of a vector to which is equivalent is negative and the other end is positive. One is in, the other one is out.
Hmm.
It means fundamentally that universe is pulsative. And we'll find it everywhere. That is a fundamental relationship. That was my thought. I leave it to you to ponder on. I'm through.
Okay,
Steve.
you're complete. All right,
I will
very
spend
good.
my 2 minutes, yes.
Okay, and Joe just put some stuff in here about language and force-based models. And that
Yeah,
is,
I mean, I think that this could be really interesting. It could be a breakthrough. I'm going to run it by some of the guys that I've been working with. Yeah, I mean, it could be using kind of, Bucky's ideas to really kind of articulate the distinction between using words versus shapes to communicate ideas. It's I mean, it really makes sense because even if you look at it in terms of how if you look at subject verb object, it's close, it's not the same thing as an RDF triple, which is subject predicate object, but there's a linear logic to it. Whereas, if you have something shape and color based, the meaning's conveyed more in patterns, and it's not linear. It's like it's multidimensional. So
It's not. Yeah.
what's that?
I
Yeah.
said definitely it's not linear. Nothing is linear.
That's right.
Nothing.
That's right. So
Also,
and then-
part that is connected to the idea of what's the difference between sort of saying, how do you feel today? Or how are you feeling? And what kind of shape are you in today?
Yes.
yeah.
What kind of pattern are you today?
Mhm.
We
Yeah,
should
what kind of
start
pattern?
speaking at them. Yes.
And that's interesting in and of itself because it requires a little bit more nuance. It's not just a reaction. You have to explain what it is, and that's what it captures as a concept that you have to actually articulate. You're thinking more in terms of concepts and not necessarily in just kind of raw emotion for that matter.
well, and this goes
so-
back, I'm sorry.
No, go ahead.
Are you okay? Are you complete?
Yeah, I'm good. I'm good.
In a way, this goes back to the whole concept of Gödel's theorem, where when a person thinks, when they imagine, when they're using their thing, they think in pictures. Most of us think in pictures. Then we translate those pictures into words, and words can't describe the pictures. It's Gödel's theorem. As soon as I take my image that I have in my mind, I translate it into a formula.
Mm-hmm.
There are some images I cannot translate into formulas. There are some things that mathematics cannot prove as true, even though they're true, and math can't prove it. So it's the very same idea, the very same concept. So
You're
I've
still
taken,
recording. Right.
I've taken that and I've stuck it on a sheet, and I'm going to be looking at it because language is a critical thing in my book, Joe.
Well,
Okay.
and that's something I would really like to explore. And you're still recording, right?
Yeah.
Because that last point that you made was actually really important.
Yeah.
This
And one thing,
statement is false. Oh, yeah.
Yeah.
Are you complete, Joe? I
Yeah, I'm
didn't hear
good.
what you
I'm
just
good.
said.
I was just going to say the idea this statement is false, therefore it's true. Then, but you're using
That's
words,
right.
And so that you
Right.
have that. But if you're thinking in terms of patterns,
Yeah.
there's nuance there.
Yeah.
Mhm.
So thought and space has shape,
Mhm.
Yes,
and
there's
Yeah.
such thing
words
as a geometry of thought.
and
There is
words
something.
are like math. They're incomplete.
Yeah.
Right.
Yeah.
So in the
Well,
beginning,
Okay.
it's the
well,
shape.
You're
Mark,
waving
when you
your
say
hand,
that,
Manu. Go
when you
ahead.
say that, I object to it, see, because math has never said that it is definitive. Math is adaptative. It's a system. Mathematics is adaptative. It reaches certain stages where you feel like, oh, I'm there. I can describe everything. But no, it is what you know is infinitely small in comparison to what you don't know. Therefore, what you structure is very small in comparison to what to come.
It's very
It
small in
is
comparison to what? Could
to
you
what
repeat
is
that?
to come, what you don't
Okay.
know.
Yeah.
Okay. And then I was adding this thing. I wanted to add before I forget about it. In terms of AI, a lot of people now are talking AI everywhere. At the beginning of it, last year or 2 years ago, I was apprehensive. What is this AI? But the reality is this one. The finer you get, the finer will be the coexistence of duality, of the pulsation. Whatever you divide will be have to obey to the law of multiplication by division. You can't. So you cannot have a world that is completely insensitive. Let's just say let's say like no feeling. There will always be the nuance of feeling. Whatever the result of a calculation of a code division is, you always have a dual part that coexists in whatever infinite division that you can take. And to me, it's the fundamental. That is the definition of a general principle.
Mm.
It is true everywhere. True everywhere. So whatever a division. So you cannot leave to say, I will divide, I will divide, I will divide. I will do my AI is going to go and come in patterns. You're exposing yourself to black swan. Practically. Because there's something that will happen in the background that you're not unaware of, and it will come swinging and hit you bad.
Right on.
That was what, yes, that was,
Okay.
yeah.
We're now almost 15 minutes over time. We've been here for 2 hours and 15 minutes. I'm ready to leave.
The fault is mine. I'll buy the beer.
All right.
All right. See you next
All right.
week.
Take
Okay,
care, everybody.
thanks.
Bye
Later.
bye
Bye.
all.
Bye-bye.
Richard,